Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Kanimi bin Halim. I'm going to present design and analysis of last first mapping and backward search module for the DNA sequence accelerator using bow-tie algorithm. I'm from ERA UiTM. This is my presentation outline. First, I will present the introduction. Then I will present the problem statement, objective, methodology, design discussion, and conclusion. LF mapping, which stands for last first mapping, is a key component in Borrow-Wheeler transform-based indexing and search algorithm. It establishes a correspondence between character in the last L and first F column of the Borrow-Wheeler matrix. Specifically, the ith occurrence of a character in the last column corresponds to the same text character as the ith occurrence of that character in the first column. This property allows efficient navigation through the transform text. These are the problem statements in DNA sequence alignment. The first problem statement is escalating mapping complexity. Existing bioinformatic tools are increasingly overwhelmed by the exponential growth of mapping seed data. Large-scale sequencing demands scalable and adaptive indexing strategy. Second problem statement is resource-intensive alignment. Aligning short DNA read to massive reference genome remains computationally intensive. High throughput environment amplify latency and memory usage concern. The third problem statement is suboptimal algorithmic efficiency. Traditional alignment algorithms struggle to optimize CPU and memory utilization. This bottleneck hinders speed and accuracy in large-scale genomic workflow. This is the objective of this paper. The first objective is to design last first mapping and backward search module. We will design the custom hardware accelerator to optimize the performance of core computing stage in bow-tie. Second objective is to develop accurate HDL model of the modules. So we will use Verilog HDL to model the behavior of the module that we want to design. Third objective is to synthesize and evaluate with quarters. We will analyze and synthesize the RTL design using quarters prime in order to validate the timing, resource utilization, and logic efficiency. The last objective is to validate with model sim. We will simulate and test all the modules that we have designed using model sim to ensure the correctness and its functionality. This figure shows how last first mapping process works. Imagine there is a query of a subsequence AAC that need to find the sequence in the BWT matrix. First, the last character C will be searched in the first column. We see that there is 2C on the left, and there is a top C and bottom C. From there, it will see the last column, and it's supposed to match the second characters in the query, A. So it will use this A top and A bottom to find the next A in the first column. So at the second stage, it will compare whether the query AC is similar in this A top and bottom, and the second character must match the AC character of the query. So if both AC and top and AC bottom is equivalent, we goes to the last column. So based on these two, it shows that the only option for the next search is the last column with a bottom, because the dollar sign indicate the starting of the sequence. So this one gonna be wrong. So we will take this a bottom and we will search back in our first column, this one, and then we see that this is our matching subsequence AAC. So the whole sequence that going to be transferred out is the AAC, and then we take our $AC together. So it means that this is our original sequence that need to be searched with subsequence search. Okay, this is how the backward search process work. Usually we will use this in order to reconstruct our sequence in full. So first we will start from the first character in our last column. So the first character in our last column is G. So from there, we know that we will go to the first column and we will go to the same character G in the last place of our first column. From there, we see the equivalent character in the last column of the first G is C. So it means that the next character after G is C. And from there, from our first C in the last column, we will search our equivalency in the first column. So now we go to our first column, and there's a 2C. We take the second C, because we know that the C in the last column is equivalent to the second C in the first column. And from there we will find the equivalence character that is at the same position of our C in the last column, which is A. And then from the last column, we go back to our first column, and then we find the equivalent A in the first column. So there's a 3 A's in the first column, and we know that this one is equivalent to the third A in the first column. From the first column, we go back to our equivalent position of A in the last column, and then that's gonna be our next character. So now the character now is AACG. So from the last column, we will find the second A in our first column, and we have 2A. So we know that the A that we previously searched is equivalent to the first A in the first column. So we go to the A in the first column after the dollar sign, and we'll find the equivalent character that in the last column. From there, we find C in the last column, and we know that this is the first C in the last column is equivalent to the first C in the first column, right? And we go to the first column, we go to the equivalent C in the first column, we find the equivalent A in the last column. And from there, we finish the sequence reconstruction using the backward search process. So the final sequence that we reconstruct is ACAACG. This one shows the flowchart of our design process. So when we establish the specification, we will design the hardware and we will test that in the model shape. So if the functional is correct, we will synthesize the design in the quarters. This is the block diagram of our LF mapping and backward search for multi-DNA sequence accelerator. It consists of two blocks. One is the LF block, another one is the backward search block. So we have this input query to the LF blocks, and we have the S1, S2, S3, S4, S5, which represent the value of our multi-matrix. Both will be fit into the LF block and also the BS block. So in the LF block, it will perform the operation to find the sequence based on the fragment of the sequence and take out the equivalent sequence. And then in the backsearch module, it will perform the backward process and it will reconstruct all the sequence from the beginning until the end and produce the original sequence. This is the result for LF mapping top module. The RTL is correctly synthesized where all the LF1, LF2, LF3 is being produced and all the input and output are correctly wired and the modules works perfectly. So from the report summary, we see that it use 9 combinational module and 10 dedicated flip-flops. In terms of functionality, we see that when the input query is inserted, right? So it goes through the LF1, LF2, LF3, and the sequence produced in the final result correspond to the correct sequence in full based on the sub or partial sequence in the query. So the result is correct in terms of the simulations. This one shows the backward search top module. From the RTL, it shows it's correctly produced the backward search module 1, 2, 3, and 4. So all the synthesized RTL are correctly generated and wired as per our block diagram. So there are 113 combinational logic, and we have around 90 pins generated for the RTL. From the simulation, based on the outputs of A, B, and C, the final output of the BS4 produce the right original sequence, which means that the design is functionally correct. This is the conclusion of this project. So this project has successfully achieved its primary objective by designing and analyzing hardware accelerator for key components of the multi-alignment algorithm, especially the LF mapping and backward search block. So the implementation of the HDL meet the initial design specification, demonstrating the potential of significant performance improvement in DNA sequence alignment when we optimize that. And through rigorous analysis and synthesis using quarters, the HDL code was effectively transformed to the RTL and it allows for the detailed optimization and timing analysis. The functionality and the timing of the model were meticulously tested and validated using model sim, confirming that the HDL implementation is functionally correct and timely accurate. Thank you very much for listening to my presentation.